creating graphs of sequences, and then also how you can graph this particular sequence. So some computer algebra systems have special commands that enable us to create sequences and graph them directly. And with most graphing calculators, however, sequences can be graphed by using parametric equations. For instance, the sequence in example 9 can be graphed by entering the parametric equations. So recall parametric equations, we just add another parameter, so x equals to t, and we'll have y equals to t factorial. Divide this by t to the power of t. And then after setting it to parametric equations and then graphing in dot mode, starting with t equals 1 and setting the t step equal to 1, we can graph it, but I'm not sure which calculator my calculus book was referring to. This is from my calculus book, but the trusty Desmos graphing calculator always has a way to graph just about any function. Here I've set up how you can graph it in Desmos Graphing Calculator, and so we could write function a of x equals to x factorial, divide this by x to the power of x. I've hidden this otherwise it will show the function around like that, and we'll use it as a function. Then what we could do is graph. This is going to be a parametric equation actually, but the way this way set up, you put n and then in a bracket a of n, so there's the x, there's the y, but then you could set up a list here. So if you write n equals to bracket 1 comma dot 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 and then all the way to n, it shows a 100. Then I have set up capital N equals to 100. So we have a 100 element list, and all this stuff is just 1 2 3 4 all the way to 100. And as you can see, we have a sequence like this, and it converges right to 0 very quickly. And let's just click this and play around with this graph. Very fascinating stuff. Alright, so here's the graph. I'll just make this projector mode, so sticker. So notice what we have here. There it is. It converges. And again, if you change this one right here, whoops, let's change this back. So if you change this one to 10, notice then it just removes all of those over there. And then put another one there, and so on. You could just hide the axis, remove the grid. Anyways, you can do a lot of other stuff there. So it's very fascinating stuff indeed. And if you click this, it shows that function. That's just the function. That's an interesting point over there. So anyways, that's fascinating stuff indeed. And you could hide these, and then let's see, I'll cover it and move it up, and it moves around. So anyways, that's pretty cool stuff. Play around with that calculator. Very fascinating stuff. So yes, the graph converges very quickly to 0 after about the 10th term from here. Hashtag nice. Alright, so now let's look at another example. This is example 10, and this one we're asked, for what values of r is the sequence r to the power of n convergent? So this one here is very interesting. I've actually covered this in my earlier videos, so I'll just put a recall. Yeah, recall that for setting this in function mode, limit as x approaches infinity of a to the x, this is equal to, I'll put this big like this actually, like that. This is equal to infinity if a is greater than 1. So if it's greater than 1, then you're going to have a power or a number to the power of infinity, which just keeps going, a larger power, it keeps getting bigger and bigger and bigger, so it approaches infinity. But this equals to 0 if we have a fraction that is, well, a, where it's less than 1, but greater than 0. So yeah, so recall that, well, for example, to illustrate this point, for example, if you have a 1 to the 1/2 or 0.5, that's in between there, then to the power of infinity, this becomes, well, 1 over 2 to the infinity, and then this becomes, well, 1 over infinity, and this goes to 0, and so on. Just put a little illustration there. Yeah, so thus we can replace a with r and x with n as with theorem 1. So because if it's the same function, but then in integer / sequence mode, it'd be the same thing. So we'll have limit as n approaches infinity of, instead of a, we'll write, I'll just write r to know that we're dealing with a different one. And also because, we're dealing with r there. Yeah, my bad. So we have r there, r to the power of n. And now this, is equal to, if we have to put an equal sign there. So this equals to, and then this opens up. And then we have infinity if r is greater than 1. And it's 0 if r is a fraction. Is a 0 less than r less than 1. And since we're asked what values of r is this sequence convergent, well, 0 is convergent, So we have this value right now, where r is between 0 and 1. And now let's consider the trivial case r equals to 1. Let's put this in another space. So r equals 1 and r equals to 0. So for r equals to 1, what we have is a limit as n approaches infinity of, well, 1 to the n, that is just, well, 1. So that is convergent as well, so we have a value there. And now for the other one, other obvious or trivial or obvious one, for r equals to 0, what we get is the limit as n approaches infinity of 0 to the n. Now, well, that's still just 0. And that's also convergent. So we have this, this, and this one. And now let's look at the other case where it's a fraction, but it's a fraction, but on the negative side. So if we have r as a fraction or a decimal place, or just a number, it doesn't need to be a fraction. It's going to be less than 0, but greater than -1. So it doesn't need to be a fraction. I just want to clarify that. But you know what I mean, or you should. So if we have this case, then recall again that this just means that the absolute value is, well, greater than 0 and less than 1. So that's just absolute value. So we could just apply theorem 2. So thus, limit as n approaches infinity. So n approaches infinity of absolute value of r to the n is equal to the limit as, well, n approaches infinity, and this is the same thing as putting r absolute value to the n like that. So these are the same things, always going to be positive, so this will literally just act exactly as over here. So thus this one is going to equal to, well, 0. This is the same thing as this one above here. This part right here where 0 is between where r is between 0 and 1. So thus this is convergent for the values. Or I'll not circle this one, I'll leave the circling for applying the theorem. So thus, by theorem 2, since the absolute value of the sequence is 0, or the limit is 0, so too is the sequence itself. So thus, limit as n approaches infinity of r to the n is equal to 0, like that. And now the last one is if r, so if, I'll put a better line, oops. So if r is less than or equal to -1, well, then this one is obviously going to be divergent. Then Rn is divergent. And this is as in example 6 that I covered earlier, as in example 6. And we can scroll all the way up there to example 6 just to recap on. So this is example 6 right here. Remember that these ones, this is for r is -1. This just goes back and forth. So -1, -1, positive 1, -1, positive 1. But when this is less than that, for example, if it's 2, if it's -2, then we're going to have just, all it's going to go is further up. So -2 to the power of 1 is going to be -2. And then -2 to the power of 2, that's going to be, well, positive 4. So it's going to be bigger and bigger. It's going to actually go back and forth, but even farther out to infinity. So that's also divergent. So yes, let's scroll back there. And now to illustrate all of these points, I'll just graph these out. So the following graphs plot various values of r. So let's look at where r is greater than 0. So for it's positive. So for r is greater than 0, what we end up having is, draw this box better. Yeah, then what we have is, let's just graph this out like this. This is going to be n. This is an, like that. And let's graph the first point. R is 1. So r is 1. Well, we know that when r is 1, it's all the values are just 1. Scroll up here. This one, an, is just equal to 1. So then we have just 1. Like that. Any point we go is just going to be equals to 1. Yeah, just put those there, just fix up the axis. So this is going to be 1, 1, 1, and this one is for r equals to 1. And the next one is when r is greater than 1, well, that's over here goes to infinity. So we'll just have a point here. So if it's greater, it's going to be somewhere like this, and it's going to get bigger and bigger. For example, if it's 2, 2 to the power of 1 is just 2, to the power of 2 is 4, to the power of 3 is going to be 8, and so on. So it just gets bigger, and yeah, exponentially bigger. Let's draw this a bit better there, just to fit in this graph. So this all the way here, r is greater than 1. And then lastly, for this one, we have when r is between 0 and 1, this goes to 0. So yes, as you see here, 1/2, and then it just gets bigger and bigger, bigger. So then we'll have starting here, draw this in blue, and it just gets smaller and smaller, like that. And this one is r is this is r is between 1 and greater than 0. And now let's look at the case where r is less than 0. So for r less than 0, and we already know what the case. Yes, so right, this here we already know the case for r equals 0. That is just 0, as I showed above here. So for r equals 0, that's a 0. That's just a point on here. This is r equals to 0, and then we'll have a point everywhere. Actually, r equals 0, like that, and so on and so on. So we just ignore those. So yeah, that's just a trivial one. So is r equals to 1. Yeah, but anyways, let's graph for r is less than 0. So actually, if we have these ones all the way there, let's add this for greater than or equal to 0. It's equal to 0 there. Yeah, so now let's graph for r is less than 0. So this one, because it's less than 0, it's going to be alternating across the axis. So we'll make it in between this x-axis like that. This is the n, this is a n, and then let's draw the one we know, the one we solved earlier. This is 1, this is negative 1. So for r equals to 1, r is negative, r equals negative 1. So negative 1 to the power of 1 is going to be, well, negative 1. Negative 1 to the power of 2 is going to be positive 1. And then as you can see, it just keeps going, alternating across, and it's divergent. And it goes down like this. And then lastly here, and this is at r equals to negative 1. And then the next one we'll draw is, well, when r is less than negative 1, remember that is just divergent, and this is just alternating, but even further. So for example, negative 2, it's going to be negative 2 to the power of 2 is going to be, well, the power of 1 is going to be negative 2. Negative 2 to the power of 2, that's going to be positive 4, etc. So it just gets bigger and bigger. So I'll just draw something like this, goes there, and then it alternates across here, and it's getting bigger and bigger, like that. And this one here is r is less than negative 1. And then lastly, again, as theorem 2 showed, when r is between negative 1 and 0, that also goes to 0. So then what we'll have is, so if it's a fraction, for example, the negative 1/2, the power of 1 has to be still negative 1/2, so it's going to be negative, and it goes to the positive, so it's going to get smaller and smaller, like that. It gets smaller and smaller, and yes, smaller, like this. So this is converging down over there. This is going to be for r is greater than negative 1, less than 0. Yeah, and now the results, now we can just sum this all up, summarize it. So the results of example 10 are summarized below, and basically the sequence Rn is convergent if r is between, well, it's greater than negative 1, or less than or equal to 1, and is divergent for all other values of r, and the values of the convergence. Yeah, they are limit as n approaches infinity, Rn like this, equals 2, and then we can just write this as a giant bracket like this, equals to 0, converges to 0 if r is, well, greater than negative 1, and if it's less than 1, but remember it equals to 1. So anytime it's between, absolute value is less than 1, it's going to be converging, and then this is the r equals 1 is the other one over there. And that equals to, 1 if r equals to 1. So move this around here and write if.